Hello, we are going to examine foundations in this video, and we will cover the functions of foundations, the properties of ground, footings, types of foundations, such as single pad foundations, and we are going to learn how to do the excavation and support the side surfaces of the soil, continuous and raft foundations, and deep foundations. Let's start with the functions. What is a foundation and why do we need it? As you remember, this is the classification for the building products. However, we can use the same logic in order to make decisions hierarchically for a building, especially for a functional building. We start with the building mass. We make decisions about the geometrical form, its visual aspects, colors, transparency, and that's our ultimate goal. In order to create that object, we need to make decisions about the units. These are the living areas. They can be closed, semi-closed, or open areas. And we need to make decisions about their sizes, their heights, their relationships, their locations. And some of them can uh, serve for a specific function. And we need to create a safe and sound environment for the user. We need to protect them from the negative conditions of the outer environment. If it's cold, we need to provide a certain level of warm for these units, warm temperature for these units. We need to protect them from rainwater and noise, probably, uh, things like that. And these living areas can serve for a specific function. Some of them can serve the users to prepare their food. Some of them can provide a safe and sound place for them to sleep, uh, things like that. And the combination of the units will create the building itself. And if we want to create a nice building to provide all these functions, either specific functions or general protection functions, we need building elements. These are the integral products that are formed by combining the materials, pieces, and components to physically meet one or some of the functions of a building. Those functions, preparing a food, protection from noise, protection from heat transfer, things like that, such as walls or roof or floors. And as we apply these different products on top of each other because of the gravity or because of the environmental factors, there are loads. These can be vertical or lateral loads. There are different types, dead loads, live loads. So we need a system to keep the form intact. This form of the building and the positions and the locations of the units intact. And this system will meet the loads, carry them, and transfer them safely. That's the building structure. We need to design the building structure based on our previous decisions about the building itself and the units. And the loads will start with the top at the top. All these loads affecting the roof or the floors will be transferred to the beams or horizontal components, the structure's horizontal components. Then they will be transferred to the columns. Each one has their own weight. So at the end, the total weight all the loads will it needs to be transferred to the ground, to somewhere. That's the superstructure. So we need a system, another system, a new building element in order to support that superstructure. Uh, a system to transmit all the loads to the ground. And when we say ground, ground is zemin in Turkish, the soil, the earth that we are using to construct our buildings, a piece of land, that's the earth. Uh, that's where we are going to put our buildings on. And We need also a system to anchor the superstructure to the ground. Otherwise, the building can slip or sway uh, if you don't anchor it. So for these, mainly three functions: support the superstructure, that's the superstructure, the part of the building that is above the ground level. Uh, we need that system to transmit all the loads to the ground itself and anchor the superstructure to the ground. That's the job of the foundations. We need foundations. It's a new building element and it needs to be integrated with the building structure. And foundations will form the substructure of the building that is below the ground level. Uh, it's here. Generally, it's because it's buried in the soil, in the ground. We don't see it, but if we just imagine removing the ground for a while, this is what we will see probably. And there are loads. The loads that comes from the superstructure, all the loads, the sum of all the loads. So our foundations needs to meet and carry these loads, and the foundations they need to transfer the loads to the ground here. But there are some additional loads, such as the pressure imposed by the surrounding soil mass and uh, most probably because there is water underground, uh, the pressure imposed by the surrounding groundwater, and this can be either lateral or upwards because of the buoyancy of the water. If we don't anchor the building to the ground as we need to, uh, that can be the end result that there is a risk of that. This is an example from China, I guess. During the construction of this housing blocks, probably these are housing blocks. As you can see, they finished the construction of the building and they were uh, doing the landscape uh, construction, and they wanted to create this underground car parking area. They excavate the ground, and because of a very heavy rainfall, there was this unsupported part, so the building just fell down like this. Uh, and this is an example from the 2023 earthquake in the southeast of Turkey. There is no problem with the superstructure, uh, but it just fell down uh, because there is no enough length uh, downwards. The building uh, uh, hasn't been anchored as it's supposed to be. Uh, How does a foundation transfer the load safely? We need to take a look at the properties of the ground and we need to learn the concept of footings. Uh, Ground or soil, it's zemin, toprak in Turkish. That's why we call it the entrance floor as the ground floor because it's the floor that is connected with the ground. When we take a closer look, we see lots of tiny particles uh, there. Uh, and because of these particles, there are gaps in between them. So the basic properties of the ground is it's porous and it's granular. Porous means gözenekli. There are lots of gaps in between these uh, particles, and they are called grains. Grains, tane or dane in Turkish. Tane, they are the same word. But in this terminology, in the engineering terminology, they are calling it dane. the same thing. Uh, Grains are formed as the rocks break down into smaller particles due to either natural causes or artificial causes. And all these coarse and fine particles, they exist in a mixture, and the gaps between them are most probably filled with either air or water, or there can be organic substances uh, such as uh, the minerals. This mixture is made out of mostly the minerals. It's like 44, 45%, almost the half of the mixture. When we say minerals, it's the substances that create the stones, the rocks, such as calcium carbonate. Each one has a specific chemical formulation. And that's it. That's the substance that we call limestone, kireç taşı in Turkish. Or another example can be this. It's calcium sulfate, and it's the substance, the stone that we know very well, gypsum, alçı. There can be air, water, or organic material like the dead leaves that animals or parts of these living once living substances. Uh, when we take a look at the grain type, we see four different categories. The first one is gravel. It's this. It's not a specific type of natural stone or the name of the stone, but the size. When we say gravel, it defines a specific size, grain size. Uh, Mostly it's between 75 millimeter to 2 millimeters. If a particle, a grain is in between 75 millimeters and 2 millimeters, that's what we call a gravel, çakıl in Turkish. Sand, kum, it's the same substance, same mineral or a different mineral, it doesn't matter. Again, it defines the size, grain size, diameter, 2 millimeters to 0.075 millimeters. These are called sand, kum. Silt, again, silt in Turkish, no difference. 0.075 to 0.002 millimeters. And clay, it's the smallest one. It's invisible at the scale. Kil, uh, the same substance. As it gets smaller, the category, the grain size category will be different. The diversity of properties may change vertically as well. As we go deeper, we can find different layers. These are called superimposed layers, layers that are placed on top of each other. There can be an organic matter at the top, and the lower part can be called the subsoil. There can be rock formation or the different layers of different grain sizes. And also there is water. That's the water that has been infiltrated through these grains. And at a certain level, because of the impermeable layers like the rocks or different types of grains like silt or clay, they create this impermeable layers which holds the water, and there can be ground saturated with water. That's what we call the groundwater, zeminaltı suyu, and that level is the water table. It's defined as the water table. Uh, However, even if there is no water in its liquid state, there is always humidity in the ground. As we construct the building, a certain level of loads due to the weights of the building products, they begin to affect the ground because of the granular structure. They start to get compressed. Uh, that's the This can be a section. So this is the ground, and that's the building. As we construct the building, it means that we are imposing weights over this ground, over these grains, and they need to resist back. that's the that's what we call a bearing capacity. And different areas can have different bearing capacities. That's taşıma kapasitesi. The ground has this certain level of bearing capacity depending on the type of the grains, the existence and volume of the air, water, or organic matter. Some uh, types of the ground can be compressed more. Some can resist more. But if the levels of the loads that we apply because of the building construction exceeds the bearing capacity, then there can be collapses or sinkholes even. This is something that we need to avoid. And even if we provide a certain level of bearing capacity, because of the granular structure, there can be some consolidation. These different grains can be compressed. The air, because of the air and the gaps in between them, and in time, building will settle. It will settle down. That's what we call oturmak. As you can see, it happens generally quickly and very, very slightly. We don't even realize that. Uh, and that's what we call the settlement, oturma. Uh, it's the gradual subsiding of a structure as the soil beneath its foundation consolidates under loading. And that's normal. That happens all the time in all types of constructions. As the building is constructed, as we apply more and more loads over the ground, some settlement is to be expected. And as you can see, it generally happens very slightly, very quickly, and uniformly. Every part of the building will settle equally. Uh, that's what we are looking for. That's what we call a uniform settlement. And it mostly happens where there are coarse-grained grounds like gravel or sand. However, if the settlement is large, if it's slow, it happens in a long time, during a long time. And if it's not uniform, if it's not the same in all parts of the building, if there are differences between different parts like that, that's very bad. That's something that we need to avoid. And that is mostly happening in fine-grained ground like silt or clay, or if there is water or moisture in the ground. Uh, and this is obviously very bad. Differential settlement can result in failure of the structural integrity of the building, obviously. Even if it doesn't harm the structure, there can be some flooring problems or the building products, they may break down. It doesn't matter if it's indoors or outdoors. These are harmful things, and especially it's bad for the structure if there is differential settlement, failure of the ground beneath certain parts of the building, then it will end in the failure of the structure like that. The building can collapse down. And this is something very important that we need to uh, be careful about. And in order to avoid that, we need to first understand the properties of the ground. The first thing that we need to do is to search for the properties of the ground. That's the soil, and that's what we call a geotechnical survey or a soil study, zemin etüdü. It can be uh, like that. We can just create a test pit by using a shovel or a mm, loader like that, excavator loader like that. And the test pit, it's generally small. It can be 1 or 2 millimeter, 2 meters wide, and most probably the 4 meters depth. Or if we need to go deeper, then instead of a test pit, we can do boring. That's what we call sondaj in Turkish. and we can go deep like 30 meters. We just create a hole for a 75 millimeter diameter. That's the test pit, an example for the test pit. And this is the machine that we can use in order to do the boring. And when we take out the machine, we can have these examples for the properties of the grains throughout that depth. If we want to avoid this result, then we need to do not just one boring, but many different borings throughout the uh, area that the building will occupy. And based on the properties of these different areas, we can either design our foundations accordingly or provide some uh, uh, certain things in order to make this ground more strong. Um, Here, that's the superstructure. If we design a skeletal structure for our building, then it means that we will have these columns which will have the collected loads. And we need the foundations, the substructure, and obviously we need columns. These will be the foundation columns and each one will end uh, on a piece of ground, and they will transfer the loads to the ground. However, because of the sizes of these columns, uh, when we apply the loads, there is this probability with the even if there is no problem with the bearing capacity, they will be buried inside the ground like the nails as we apply the loads over that. So we need a system, we need a solution, something like this. These snowshoes, these are like rackets. People put them on their feet, and by this way, they won't be buried, their legs won't be buried in the snow. It's same with the camels. Um, in this desert, with these all sand particles, the feet of the horse will bury down, and it will be very hard for the armies in the old times to travel from one place to the other through the desert with the horses. However, it's not like that with the camels because of their anatomy, their physiology of the uh, their food. We can create something similar if we end these foundation columns with a pad like that. That's what we call footing. In Turkish, sömel, ampatman, or pabuç. We mostly use sömel. And it doesn't matter if it's a single column or a shear wall, the same principle will apply like that. Even if the wall is long in one direction, again, there's this risk of burying down. So we can provide footings, a longer footing for the shear walls as well. And with these footings, the loads will be distributed over an area of the soil that is wide enough that the bearing capacity is not exceeded. If we have, let's say, the total load, uh, let's say it's A, uh, and if you create the footing, the load will be spread, distributed. That means that it will decrease. Uh, all these different parts will apply loads that is lower than A. And we know that there's always water in liquid or vapor form in the ground between soil grains, and we are doing this construction of the foundation columns and footings out of reinforced concrete, and we know that concrete is a material like that, it's porous. There are pores, micropores inside the concrete. So all this water, either in liquid form or gas form, will fill uh, all the gaps in between the grains or in the concrete. And if it freezes due to weather conditions, it expands. The water will expand as it freezes. So there is this risk of moving the footings or exploding the footings. So we need to protect our footings. We need to locate them deep enough where there is no risk of frost action. Uh, that's what we call the frost line. The footings needs to go deeper than the frost line or frost depth. Don çizgisi, don derinliği in Turkish. In old times, again, if the armies want to conquer a castle, they do this. They start digging tunnels into the ground so that they can conquer the castle from inside. However, especially in the north countries like Russia, uh, since it's very cold, uh, soldiers won't be able to dig the frozen soil. That's why they boil lots of water and they pour this boiling water on the ground so that this soil can soften for them to dig. And they can, once they are deep enough, they can keep digging without any restriction. This is how it happens. Let's imagine it's cold outside. It's minus 10 centigrade Celsius, and we want to keep the indoors warm. It's plus 10 centigrade Celsius. However, if you go inside the ground for a little while, this layer of earth will start to provide a certain level of heat insulation. As you can see, even if it's minus 10 in the atmosphere above the soil, the subsoil at this level will provide a plus 12 centigrade Celsius uh, degree, and it doesn't change during the summer as well. As it gets very hot, like plus 34 centigrade Celsius, this time we want to keep the indoors cool. Again, at that level, the temperature is constant. It doesn't change. Again, it's plus 12 centigrade Celsius. So that's how we can understand the frost line. Uh, we need to go deeper than that. Our footings, the upper level of our footings can be at this level maximum. And this frost depth can change according to the location, geographical location. And uh, with the soil study, we can understand how deep that we need to go down. Also, this depth can be identified in the regulations. We can search for the regulations. Uh, what kind of different types are there in terms of foundations? Uh, that's the first type, obviously. We need to find the depth that is safe for us to construct our footings. And obviously, at this level, the upper surface of the ground, that part, needs to have the required minimum bearing capacity. And if we provide that, then we can dig down for our foundations based on the frost depth and to anchor the superstructure. And if it's close to the upper surface of the soil, then we call it shallow foundations, yüzeysel temeller. However, there can be some cases where the bearing capacity is not enough at this level. And if we have boring to understand the properties of the grains, we can find the high level of bearing capacity way down below, like that. Uh, and in these cases, we need to construct deep foundations, derin temeller. But first, we do the shallow foundations, and the deep foundations go beneath the shallow foundations. Shallow foundations has mainly three different types. The first one is the isolated or single pad footings, tekil şömelli temeller. The other one can be stripped or continuous footings, sürekli sömelli temeller. This can be one-way continuous or two-way continuous. And the third one is the raft foundation, radye temel, radye general temel. How can we construct a foundation? Let's take a look at the single pad footings, and let's learn how we can do the excavation without any risks. If there is a superstructure column, uh, then we need to first create a foundation column in order to transfer the loads and transmit them safely to the ground. First, we need a foundation column, and beneath that, we need to have a footing. This foundation column needs to rest on a footing here, like that. That's the soil. This is the superstructure, the column in the ground floor. On the ground floor, we know that there is a foundation column, and we need to create a footing. But first, we need to excavate the ground. Excavation means kazı or hafriyat in Turkish. Let's take a look at the dictionary, Turkish dictionary, hafriyat. It's an Arabic word. Uh, Please don't be confused with uh, saying these letters in the wrong order. It's not harfiyat. Harf, it's something else. We are talking about hafr here. It's the root of the word. Okay. We excavate the ground like that. We do the construction, and once we are above the upper surface of the soil, then we put all the earth back. We bury this foundation. Uh, we need to do the construction till the grade level. We don't just do the construction uh, at the upper level of the soil. We need to find the grade level. The grade level is su basman düzeyi in Turkish. It's this height. Uh, and that depends on your decision. That's the upper surface of your ground floor. That's where we call 000 as the level. And that height, it depends on our decision. If we are looking for three steps and each step is 15 centimeters, then this level will be 45 centimeters. If this is 0 level, then the upper surface of the earth will be minus 45 centimeters. But if you are looking for a higher grade level, then instead of three steps, we can go for four or five or six steps. And if we want, we don't do any grade level. The grade level can be zero, but that's important for us in order to protect the building from the water. Soubassement, it's a French word, basement, the upper surface of the basement, it means. However, when you hear the word, you just remember su basması here. That will be the building once we do the walls. That will be our ground floor, and as it rains, there can be puddles, water puddles. all around, depending on the type of the surface, the ground. And we don't want this water to penetrate inside the building, flooding. That's why we need grade level or find another solution if we don't want this height, if we don't want steps while we enter the building, because that can be a problem for the handicapped people, or there can be other risks. So we need to find a solution. We can uh, have the upper surface of this slope, the ground sloped away from the building, or we can have a drainage system. And as you can see here, that's the grade level. And without the grade level, even if there is no risk of flood, there can be this stains due to the rainwater. Uh, and we need to be careful about the slope direction. With the rainfall, this all excessive surface water can cause problems. So we can change the slope or regulate the slope all around the building. Uh, Once we do the excavation, we can do the construction of the footing and the foundation column. After that, once we are at the grade level, we put all the earth back, and we can uh, continue the construction of the superstructure, the upper column. Uh, Single path footings, tekil sömelli temeller. There are some rules that we need to keep in mind. First of all, minimum size of a footing cannot be smaller than 70 centimeters, either this direction or that direction. The minimum size needs to be 70 centimeters. And the minimum area needs to be 1 square meter. So it's a footing that is 70 centimeters to 70 centimeters will not be enough. Uh, we need to consider that, uh, give dimensions so that the total area of the footing is at least 1 square meter. That means that either this can be 1 meter to 1 meter, or if we keep it 70 centimeters, then we need to have a longer footing to provide 1 square meter. Uh, and we are constructing the footings and the foundation column out of reinforced concrete, because when we bury the earth back, when we bury the foundations, when we put the earth back, the foundations will be buried in damp uh, soil, because of the rainwaters and groundwaters. There is always this humidity or liquid water, and it's if you prefer steel or timber for the material of the foundations, it can be bad. There can be problems. So the reinforced concrete will be the best choice, and we know that there are reinforcement bars, and the minimum thickness, this height of the footing, is 25 centimeters, or it needs to be at least 1/4 of the cantilevered length. The cantilevered length is this length in two directions, in either directions, between the side of the footing and the side of the column. It's important to provide 1/4 of the cantilevered length, uh, because if the thickness is not enough, uh, then because of the load, uh, if it's not thick enough, then the column will punch its own footing. Uh, just like the this floors without beams. There's this punching risk. It's the same principle, same thing. So we need to provide a minimum thickness required. That's how a foundation column and a single pad footing out of reinforced concrete looks like. We can see the excavation as well. If it's hard to excavate because of the types of the grains and the structure of the soil, then we can have these separate excavations. We don't need to excavate the whole area, or if it's not that much of a problem, then we can excavate the whole area, do the construction of the foundations, and then put the earth back. However, it's not just the excavation. The problem is not just to excavate the area where we are going to store that soil, because we will need it later. If we don't have any area for the storage in our plot, then we need to transport all that soil with trunks to somewhere else and bring them back together. Once we excavate the area, we can do the formwork for the footings, place the reinforcement bars, then pour the concrete, and once it's hard enough, strong enough, we can take the forms out and continue with the foundation columns. As you can see, there are dowels. First, we construct the footing with the dowels. Once it sets, we remove the molds and we create new molds for the foundation column, put new reinforcement bars and connect them with the footings. And again, we need to have dowels to connect it to the superstructure columns, like that. We need these type of forms. And the excavation, it's important. The sites of the excavation may or may not resist displacement. In some sort of the soils, like rocks or coarse grains, when we excavate, the sites can hold like that without falling down. Uh, but depending on the properties of the subsoil and the depth, there can be sliding, the risk of sliding or toppling like that. And they are both dangerous. The workers can be harmed. All the construction materials can be ruined. And we don't want that. And if there's a risk of sliding or toppling, in order to keep the pit open and protect the workers and equipment, we need to support the sites. And these can be creating by sloped sites, or to construct a support system. That's a big risk. And if there's a building there, again, there is this risk of collapsing down or sliding altogether. Uh, that's where we that's the risk, main risk in the north side of Turkey. Uh, if we excavate the ground and do the excavation with these sloped sides, they can stay like that. Uh, but if you keep it like this, there's this risk of sliding or toppling. However, if we create sloped sides, then the risk can be minimum. Or if we need 90-degree sides, then we can have these support systems. This example is called sheet piling or shielding. In Turkish, we call it palplanche, uh, that one. And that's creating some sort of wall that can hold the resistance of the earth, the loads of the earth. It can resist it to the loads of the earth like that. That's sheet piling. And in order to support the sheet piling, we can have shoring or tahkim. And these can be horizontal or again inclined shores, like that. So first we create some sort of very strong wall in order to support the sides of the excavation, and after that we can have construct shoring in order to support that wall. And that shoring can be horizontal like this or inclined like that. There is this short movie. Let's take a look. So they are not excavating at once. They go level by level. They just excavate to till they get a certain depth, and then they do that shoring and shielding. As you can see, they are using these steel profiles. They are all connected with bolts. And first they create the wall, and then they create these shores in order to support the wall, and then they excavate a little bit more because as we get deeper and deeper, the pressure of the earth at the sides will increase. So we need to have a very strong uh, support like that. And once we are deep enough, we can start doing the construction of the foundations. And that foundations, that construction needs to be calculated uh, by a civil engineer uh, like that. And using this technique, we can construct inside the water as well. These are all shielding that you can see inside the water. But when there is water, addition to the loads that are created by the earth will increase uh, because of the pressure of the water. Or we can create retaining walls. İstinat duvarı. İstinat in Turkish dayanmak, yaslanmak, sunut kökü o. İstinat etmek, bir şeye dayanmak, bir şeye yaslanmak. Senet sözcüğü de aynı kökten geliyor. İşte bir dayanak, dayanılacak, güvenilecek şey. İşte birisinden borç alıyorum, senet imzalıyorum. O senet onun dayanağı. Ben ondan o borcu aldığımı ve parayı ödeyeceğime dair bir dayanak vermiş oluyorum eline. Retaining walls is it works as the same way uh, like the shielding, uh, but instead of a thin surface, it's this wall, and it can be constructed out of stones, or we can construct these retaining walls out of reinforced concrete, something like this. One side there is this earth at the higher level, and the other side, because it's excavated, the level is lower, and we need something to hold that earth. We don't want it to collapse towards the lower side like that. So it's very dangerous. Uh, we don't want that. So we need to make proper decisions about the properties of that retaining wall. And again, a civil engineer needs to make the calculations for its sizes and the materials and the reinforcement bars and everything. We can create different shapes, different forms for the retaining walls. Since there is going to be a pressure of the earth in this direction, a lateral pressure, instead of creating a straight surface for the retaining wall, we can have this sloped inclined surface, and with only the change in this shape, in the form, the it will be harder to collapsing the wall. It will hold. Or instead of creating that sloped surface, we can go deeper and deeper. And with this depth, there will be some additional. There's this load in this direction. However, because of the depth, there will be some counter loads of the earth. It will hold. Or we can have a footing for the wall like that. It goes in other direction, and with the weight of that earth, again, it will hold. It will become harder for the wall to collapse down. Or we can have these special anchors and connect the wall to the Earth itself. And also there is this risk of rainwater again one more time. When it rains, the rainwater can build up here at the back of the wall, and in addition to the that are created because of the soil, there will be additional loads because of the water. So we need to have a drainage system. We can create a pipe, and there can be some coarse granular soil above the pipe so that the rainwater can be filtrated, and it can be collected in this pipe, in this drainage system, and we can have the excessive rainwater drained out like that. Even if we don't do the excavation for the foundations, we just want to have an open unit uh, like this. The sloping natural surface can be dangerous or unusable, unfitting for us. So instead of this risk, we can have a straight surface, and because of this level difference, again, we will be needing retaining walls like that. And that's what we call site grading. We can change the slope of our site according to our design, based on our design. We can have, instead of leaving the natural sloping surface, we can change the slope like this, uh, alter the topography. And when we are doing that, again, we need to be careful about the sizes of the excavation, sizes of the level differences. We don't want to do that. If it's so deep inside, it means that there will be lots of pressure at the back of this wall. And it won't be very useful for the users as the open air spaces. So instead of doing it like that, we can have different levels, minimal levels that will give us lots of different space alternatives. And since the height will be decreased, there will be lesser loads at the back. And if we are placing our building mass over a sloping surface like that, then again, changing the slope so much, making a very different area like this. Either we can fill uh, the whole sloping area with earth and place our building mass on top of the filled area. That means that there will be lots of pressure towards the sides, and we need to have a very strong retaining wall to do that. However, it's a risk. Even if with the most the strongest retaining walls, there is always this risk of sliding or toppling. And if there is the building over that area, then it can collapse down as well. Or we will be facing with that kind of problems like that. Uh, we see that all this area has been excavated in order to have an access for the building. They need to create that bridge. Uh, and again, there is this risk of collapsing down towards the building this time. These are not good solutions. We need to, uh, we don't want that excessive cut and fill, and we don't want to risk our building, uh, either the collapsing of this soil towards our building, or collapsing of this filled soil so that the building will slide down. Instead of doing that, again, we can have a different levels. We can use different levels and try to keep the topography as natural as possible instead of creating a very different part, excavating the whole area and filling the whole area. We can use the slope and have different levels in our design in order to do minimal cut and fill. This will be better for us because again, there are risks here. This example is from Istanbul. These are the existing settlement. You can see a very deep excavation of a new building uh, next to them, and there are retaining walls. But as you can see, it's not a solution. As the retaining wall collapses, the earth and the buildings will start to collapse down. It's a very high level of risk. Uh, the same building in a different angle. When we do the single path footing, we need to create one foundation column uh, beneath the columns on the ground floor, beneath each column on the ground floor. If there are four columns on the ground floor, then there will be at least four foundation columns beneath them. And the minimum sizes for these foundation columns will be the same with the ground floor column sizes. They cannot be smaller than that. And they need to end in footings. And these footings can be separated like that. Each foundation column will end with its own footing. That it will be a single pad footing. However, as we apply the loads, we should always keep in mind that there is this risk of separation, like that. In order to avoid that risk, we need to tie all these separate footings and separate columns with beams. And in order to tie the footings, we need tie beams. That's what we call tie beams, bağ kiriş, bağ kirişi in Turkish. And it's not enough to tie them at this level only. We need to tie the foundation columns at the upper level as well here. And that's what we call grade beams. As you remember, grade level is the height between the upper surface of the floor and the ground floor, upper surface of the ground floor. And that's what we call the grade level, su basman düzeyi. So at this level, if we tie the columns together, then we will be using grade beams, zemin kotunda kiriş in Turkish. Uh, we need to tie them in both levels. We both need tie beams and grade beams. You remember our building, that's the floor. Uh, there will be loads, the weight of the floor itself, the deadly loads, live loads, all the other loads. And we need a structural system, skeletal system with these columns, building structure, and the walls. They are just separators. We don't need them in order to transfer the loads in skeletal structures. This is superstructure. The columns, that's the grade level. These are the superstructured columns, and they are connected with beams, and there's this floor slab over that. And we know that every column on the ground floor, every column of the superstructure needs to end with a foundation column and the footing, right? So beneath the surface of the earth, there will be foundation columns, and they need to go deep, at least to find the frost depth. And that's the minimum level that we can place our footings. We need to go down. We need to excavate the ground uh, till the till that level, required level. After that, we are going to create our single paths, uh, these paths, and over that we are going to do our foundation columns till we are at the grade level, and we need to create tie beams to connect all these separate footings and grade beams to connect all these separate columns. Tie beams can be minimum 25 to 25 centimeters, these. can be minimum 25 to 25 centimeters. Uh, it can be the minimum of the height of that footing. So if we have a section, that's what we will be looking at, a square section to 25 to 25 here. That's the minimum size for the tie beams. And grade beams will be the same with the superstructure. For the superstructure, this is what we have learned. The thickness of a reinforced concrete beam cannot be smaller than 25 centimeters. The height cannot be smaller than 30 centimeters. However, it's not enough. We mostly divide the span by 10 in order to find the required minimum size, the length of the beam. The span is the gap between two columns and the length of the beam. Uh, so our grade beams will be like that. We can calculate the grade beams. This width is minimum 25 centimeters, and this height needs to be calculated based on the bigger span. Uh, we need to divide that span by 10 to find the minimum required height. Uh, what if the bearing capacity is not enough? When we do a single pad footing, as you can see here, all the loads of this column will end on this footing. On the loads will this column will end in this footing, and they are since they are separated, even if we tie them with tie beams, they are still separated, and there will be different levels of bearing capacity. On this ground area. And what if the bearing capacity is not enough? Uh, we need to change the system, uh, either doing continuous footing or raft foundations, or deep foundations, obviously. Also, the earthquake-prone areas, uh, it's not appropriate to use this type of separate single pad footings because even if we connect them with tie beams, it's not strong enough. That connection is not strong enough, and we need a stronger solution for the lateral earthquake loads. So instead of single pads and connecting them with tie beams, we can have continuous footings. That means that we can create a very long pad and have two different columns over one single pad like that. And it can be continuous in one direction, one-way continuous, or if we want, we can do this continuing thing in two ways. Instead of tying the footings with tie beams, we can have a bigger single footing like that, two-way continuous. We can make them two-way continuous. That's one-way continuous. We have foundation columns, a very long footing, and two foundation columns over that very long footing. And we still need tie beams because it's continuous in one direction. However, in the other direction, we need to connect them together. As we create a bigger footing, it means that the loads will be distributed, spread in a better way, uh, so that the bearing capacity will not be exceeded. And we still need grade beams to connect the columns at the grade level. Or instead of one-way continuous, we can create a, a continuous footing in two directions, in two ways, and we will have foundation columns. Since there is only one continuous footing, one big footing, we won't be needing any tie beams anymore because there is nothing to tie. It's just one single continuous footing. However, we still need grade beams to connect our separate columns at the grade level like that. But let's imagine the bearing capacity is not enough. It's still not enough. Even if we do this continuous footing, we still exceed the bearing capacity, or there are some other risks, like there is this underground water and it has this buoyancy effect. Then we will be needing a raft foundation. What's the difference? Here we still have a footing. It's continuous, it's big, but it's still a footing, and the height is not enough, and there is this hole gap in between. Instead of that footing, what if we excavate the ground for a little while, uh, we go a little bit deeper, and we create a very thick floor slab. And there, of course, it's the reinforced concrete, so there will be reinforcement bars. We create a very thick and heavy uh, floor slab, and over that we have our foundation columns, and the thickness of that slab uh, it needs to be minimum 50 centimeters. That's what we call a raft foundation. That's 50 centimeters. If the bearing capacity of the ground is so low, if the water table is high and there's this buoyancy of water, it poses a risk. If the columns are close to each other, so that when we do the continuous footing, there is no gap or a very short gap, very small gap in between the columns. If there is this high risk of earthquake, if the loads of the superstructure are uh, so high, then we can prefer a raft foundation. These are the main reasons to prefer a raft foundation. But we still need grade beams because there are separate columns and we don't want that. We need to connect them with grade beams uh, till we have the grade level. Uh, so that's the shallow foundations. We prefer them if the bearing capacity is enough here. We just need to go deep enough to find the frost line and go deeper so that our footings will not be uh, there won't be a problem with the footings because of the frost, and the building can be anchored uh, uh, down. That will be enough. However, if the bearing capacity of that level is not enough and the strong layer is very deep, then uh, we need deep foundations. First, we construct the deep foundations, and over that, we construct the shallow foundations, and over that, we construct the superstructure. Deep foundations, there are two different types. One is the pile foundation, pile kazık temel in Turkish, or caisson foundation, caisson in Turkish. It's something like this. As you can see, we still have the shallow foundations, and deep foundations are beneath them, like that. We have our footings, and the piles or caissons are below that footings. And if there is soil liquefaction, zemin sıvılaşması, it means that water-saturated sediment temporarily loses strength and acts like a fluid, not a solid, but a fluid. Here is an experiment made in Nide University Civil Engineering Department. Let's take a look at that. The one on the left has piles beneath the raft foundation. The one on the right, it doesn't have any deep foundations, only the raft foundation. There are different layers of soil, like the gravel and sand and clay, all mixed, and there's water. The whole part is saturated with water, and as you can see, as the earthquake happens with these lateral uh, loads, the soil starts to act like a liquid. It's not solid anymore. So the we see that the soil has been liquefied, and it ends with the building being buried deep down if there is no deep foundations. Pile foundations, there can be two different types. One of them is the end bearing. We create piles long enough to find the high level of bearing capacity layer, uç kazığı, and by this way, we transmit the loads to the level of bearing capacity layer like that. But let's imagine if it's so deep and we cannot create piles that are long enough to find that level, then instead of finding that high level of bearing capacity layer, we just have shorter piles and we rely on the friction. Uh, as we apply the loads, the soil grains will create an opposite load with the friction. And that's what we call sürtünme kazıkları. Piles can be created out of timber, concrete, steel, or composite. Composite means the mixture of different materials like the steel and concrete. Of course, timber material needs to be strong enough. The types of the trees, uh, not every type can be appropriate to bury in a humid environment in the soil because it will start to decay. But there are certain types of the trees which are very resistant against water damage. If we use concrete, that's fine. But if we use reinforced concrete, we need to find proper solutions to protect the reinforcement bars, the steel profiles. Otherwise, there's this risk of corrosion, obviously. And that's how we apply them. We nail them inside the ground by using this type of heavy machinery. Uh, caisson foundations, it's a little bit different. We use boring first. We create a very long hole in a larger diameter, obviously. And then inside that hole, we place reinforcement bars and we pour concrete. That means that we are creating reinforced concrete columns, very large columns inside the earth, like that. First, we do the boring. We create that hole, very long hole. Then we place reinforcement bars, and then we pour concrete over that to have that caissons. These are all caisson foundations. And as you can see here, we still have dovels. And over that, we are going to create our either single pad footings or continuous footings or raft foundations. And we are going to connect the reinforcement bars of the foundations with these dowels. So that's the end of our topics for this video. Hopefully, in next video, next week, we are going to examine how we can protect foundations. Thank you for listening.